let's look at an isotonic solution. Oops. Once again, we've got a solution. We've got a cell. We're talking about salt and water. Salt is our solute. Water is our solvent. In this case, isotonic implies that the concentration of the solution is the same as the cell. So that means that if the cell is 19% salt, the solution is 19% salt, which means that the water concentrations should be the same too. In that case, our movement, if one molecule moves in, one molecule needs to move out. If 15 move out, 15 need to move in. So in this case, water and salt move in and out equally. We don't need to write equilibrium. It's already at equilibrium. Isotonic solutions are already at equilibrium. Make sure you guys know how to solve these types of problems and can actually answer and figure them out. There's a worksheet for you guys to practice on the Google site. All right, this is a pretty neat video showing how osmosis can actually work for different vegetables. It actually shows a piece of lettuce and how a hypotonic solution can make water move into the lettuce and firm up a piece of wilted lettuce. All right, just some things for you guys to consider when you're watching the video. And this is just an image showing you how the water will move to almost try to dilute an area with lots of stuff. This is a picture showing us blood cells, red blood cells. Red blood cells typically have a concave shape. They're like a dented shape. In an isotonic solution, right, over here in A, all right, this is their normal. All right, this is them perfectly fine. If they're in a hypertonic solution, let's say you add lots of salt to the bloodstream or lots of sugar to the bloodstream, all right, what's actually going to happen is the water is going to start to leave the cells. And the cells are going to actually start to shrivel up. They're going to start to wrinkle. And you're actually going to be able to see the effects of the actual blood cells. Opposite, in a hypotonic solution, all right, the water is going to move into the cells. It's going to plump them up. And if they get plump enough, they're going to rupture. Red blood cells carry oxygen. Kind of important for them to be intact. You don't want them to be disrupted because you don't want to have to worry about a lack of oxygen in your bloodstream. The last type of passive transport that we're going to talk about are ion channels. All right? When we talked about the cell membrane, I referred to proteins as being the back door. The name here implies what type of molecule is going to use this back door. Ions. And if you guys remember, ions we learned about in the biochemistry unit, ions are going to be charged atoms. So when they go to the bouncer, when they go to the cell membrane doesn't let them right through. They have to go to the back door, right? They're a little too big, or they are just repelled, pushed away by the bouncer. They're just not allowed to pass straight through by diffusion. So they need a tunnel. They need a back door to try and get in or out of the cell. And that's basically what an ion channel is going to be. This picture is showing, all right, how ions are actually able to pass through the channel. You have a gate here that operates just like a door, like the back door. When you use the knock, all right, when you knock at the back door, the door will open and ions can flow through. All right, ions are able to move from high concentration to low concentration, right, so long as the door is open. So, recap our passive transport. Passive transport, no energy is needed. So the movement instead is going to be because there's a difference in concentration. So the stuff is going to want to move from high to low. We've got three types of passive transport: diffusion, osmosis, and ion channels. Diffusion is for the really small stuff. Osmosis is for the water. And ion channels are for the slightly larger molecules, slightly larger atoms like ions.